So, shall we start? Hi, everybody. So, today we want to talk about support vector machines. And yeah, I do know that nowadays everybody is interested in deep learning and deep neural networks. But support vector machine is indeed what has, it includes also deep neural networks. That's the key point. It's one of the very promising ideas that people came up long time ago. Basically, Vapnik came up with that idea. And yeah, it just made a huge difference. Now, what is the point here in support vector machine? So as you know, the only difference with what we had last week is that now we are talking about a machine. Previously, we were talking about a classifier, right? The classifier was the linear model. So just a quick recap what we have done up to this point. We talked about the support vector classifier, right? And the support vector classifier was just building this linear boundary between different classes using the support vectors, right? So you wanted to just to find the guy which is in the maximum distance from the margin, like boundary points or the maximum margin. And how did we do the training? We basically ended up with this solution that we first somehow compute the cross correlation between the points inside the data set, right? So you just check how these two are correlated, these two cross correlation between different labels. All of them, you find it. This is basically those xn transpose xm values, right, in the expression. And then we write down the dual problem. Out of that, we could just find out the support vectors, right? The support vectors were those who had their corresponding dual variable to be non-zero, right? And these are the support vectors. Now, your line is going to be a linear combination of those support vectors, right? So your model is basically given in terms of the support vector, right? And we talked about this. They are like the supports which are keeping the boundary, so this is why you call it support vector classifier. Now, if you get a new point, we talked about this one as well, we just do cross-validation again, right? I give you a new point. The thing that you need to do, of course, geometrically, you're checking where this guy lands, but the key point is that on the paper, what we saw was that you get this new point, you just compute its cross correlation with all the support vectors, right? So you compute the cross correlation between this blue point with all the support vectors. And out of this cross correlation, you are going to find out what is the class, right? For instance, here, it's going to have a high cross correlation with the red point, right? Here, with this one, it's going to have a high cross correlation. This is going to dominate the whole expression as compared to the cross correlation with the green points, right? And this is going to be classified as a point being more correlated with the red point, so it's going to have label red, right? So this is the way that the support vector machine is doing it mathematically or computationally. That's cool, yes? Okay, now, we talked about this. The thing that we want to do today, we want to take this idea and now try to somehow extend it to a nonlinear case. And through that, we're going to learn what is a support vector machine, which is a general case of this one. And also, we get the idea of kernel trick. And out of that, you get the idea of representation learning, which is actually a general framework, including the deep learning nowadays being very popular. So, everybody's cool? Shall we start? Great. OK, so let's start. So I told you last time that the support vector classifier is linear. So at the end of the day, you're just drawing a line. And this is going to work only when your data is linearly separable, right? But what if your data is not linearly separable? Just let's get into one example that we had before. So we had this particular example last time, right? Remember. And it was the problem of cat or dog. And then when we started with the SVC or support vector classifier, The whole idea was that like you had this simple data set, all the cats were on one side, all the dogs were on the other side, and then you want to draw a margin and you want to put the margin exactly in the middle, right? So it's going to work as long as they are linearly separable. What about this case? This is not obviously linearly separable, right? Now if you wanted to classify this data set here, if you wanted to classify perfectly, how would you do that? You probably would say the guys who are in the middle are, I don't know, cat. The guys who are on the edge, they are dog, right? So there is not a line or a threshold which is going to separate the two classes, but there is one, nonlinear term, which is, the term here in this case, the circle. It's not really a circle, two thresholds that are really specifying the cat points, right? So if you go ahead and you use your support vector machine, you definitely never get zero classification error, right? But the problem, at least when you look at it, is not that complicated. So probably you need to have a sort of nonlinear classifier, right? So a classifier which is going to classify, maybe again based on the sign, but this sign that is going to get, it's going to compute it out of a parameter which is nonlinearly depending on your data point. Now, looking at this problem, do you think there is one nonlinear term like this one which can do this classification for you? Nonlinear. Actually, the one I have written on the board, it can do it, right? So if you have this function, if you have this function, x2 plus 2x plus 1, okay? Or no, maybe let me just do it. Yeah, plus 1 plus minus 2, right? Minus 2. Okay. If you have this term, okay. Where is this guy positive? Where is this guy negative? Any idea? You can open up the term. You can say this is x plus 1 squared minus 3, right? X plus 1 squared is x squared 2x plus 1. You have this one, plus 1. Minus 3, 1 cancels with minus 3. It's going to be minus 2, right? You see that? Yeah? So, now if I draw it, here is x. This is the guy z, right? This guy z, okay, this is at point minus 1, so here is minus 1, and then at this point this is minus 3. So at the point 0 is going to be minus 2, right? Point, yeah, this is something like this, right? This is my z in terms of x, right? You see it? And if you look at this nonlinear function, in this interval here, z is negative, right? In this interval and this interval, in these two intervals, z is positive, right? So if I did, instead of having a line, which is going to give me only a single threshold, if I use a polynomial function, then I can start having one interval and two other intervals, right? Now, you can think that you can get into more complicated scenarios if you increase the order of that polynomial, right? For instance, if instead of order 2, you use order 4, then instead of having just one curvature, you're going to have multiple changes in the curvature, right? So it could potentially be like this, right? And then the sign could change, right? Quite often. And this means that, like here, you have one sign. Here, the sign changes. Again, here you have the sign. Here, the sign changes, right? And then you get more and more complicated regions, right? On one axis. Everybody sees that? So you get the idea why I say nonlinear, right? Nonlinear because nonlinearity gives you this opportunity to get more partitioning of the environment. Right? Questions? Okay. So same thing going to happen if you get into the higher dimension. For example, looking at this problem, well, you cannot find a line which is going to separate the two regions or the two labels, but you can, of course, draw one curvature, right? And again, for the curvature, you can say the same thing, right? So if you have a nonlinear function z, which is a function of, in this case, two-dimensional input, right? x1, x2, it's going to be a surface, right? And this surface, when it's nonlinear, then when you think about the contour where it's going to cut the z-axis and you're going to change the sign, this is going to be nonlinear, right? Whereas a plane, a hyperplane, if you draw it, is going to be always a line, right? Everybody sees that? So this is why, again, why I say that guy, that orange curve is nonlinear. It's not simply because this is not a line, because the original surface which is making that contour to happen is not linear, right? I mean, of course, there's one-to-one mapping between being line here and that hyperplane, but you need to just get the clear picture, right? So that is the contour which is coming out of that nonlinear model. Everybody's cool? Okay, great. So now let's get back to this problem of cat and dog that we had. And now in this example that we have, this is not linearly separable, right? So I have these points which are lying in this form. Bunch of them are here, and bunch of them are on the edges. And how I can find a nonlinear model which is going to do that for me, right? So I can do like what I did on the board. So I can try different polynomial functions to find out finally what is the right point, right? What is the right model? But that is quite hard, right? So you cannot find out the kind of algorithmic approach to do that. So what is the idea here? The idea is that maybe I can simply go to higher dimension. And this is basically what we did on the board, but in a more algorithmic way. To just see this idea, let's do what I did on the board for you right now in a different way. So I have this data set, right? This is my x. And this is not linearly separable, right? Now I'm going to build a second dimension. Okay? Everybody's cool? I'm going to build this second dimension, and I am going to consider one nonlinear function. For example, x squared, one polynomial. Okay? Now the second dimension is going to be gone on this nonlinear function. Everybody understand what I'm doing? So it means that instead of having this point x as my data point, I'm now having x squared as my data point, right? So what's going to happen to this point? This goes up, right, on the curve. This is what happens to this point, right? Everybody sees that? So the second guy, again, goes up, right? And so on, everybody goes on this curve. Everybody's cool? Now, looking at this guy, is it linearly separable now or not? I mean, maybe the curve is not perfect, but if I exaggerate that, it could be, right? If I exaggerate that quadratic function, then these guys are going to get into the belly. These guys are getting on the tail, right? And then there is one line which is passing through them. Everybody sees that? So what is the conclusion out of this? Maybe your problem is not linearly separable in its own domain, But maybe if you take it to the higher dimension, it's going to get linearly separable. Everybody sees that? Yeah.
Is that the same idea like in robotics as the configuration space and like moving into a different manifold in terms of...
Somehow, yes. I mean, all of them are doing the same thing, right? Even this is the same thing we do in deep learning. I'm going to mention it at the end of the lecture. But same thing in the deep learning. Like you do all the feature computation in the hidden layers, and you finally end up with a one giant hidden layer, right? That is actually the higher dimension representation of your data. And then from that one, you do your classification. That's the same. Everybody's cool? So what is happening here is that it's true that I cannot classify my data perfectly in its own domain, right? But I can do the classification perfectly by a linear model in the higher dimension, right? So this is the main idea that I can do. If I start from X, and then I somehow map it to the higher dimensions, now I'm building X tilde, and this X tilde is two-dimensional vector. X is the first entry, X squared is the second entry. Okay? Then this guy is capable to be linearly separated, right? Linearly classified, right? So I'm going to get my data points x's, and I'm going to replace them with this new vector x tilde, which I can directly compute from my x, right? And now I perform my linear classification on this new vector, right? Everybody's cool? Questions? No question? Great. So, nonlinear model in low dimension, it could be linear in higher dimension, right? And you can extend this idea to any problem. For instance, I guess I have it next. Let me show that. Okay, I don't have it here. Okay, I'm going to explain it later. Okay, so nonlinear in low dimension, it could be linear in the higher dimension. And this is what we call it the feature extraction or feature embedding technique. So you get your data X, and you would say, OK, it's too complicated for my linear classifier to understand it. So maybe I extract the feature out of it, right? And the feature that I'm extracting is extracted by this embedding function phi, right? So phi is essentially an embedding, which is taking your data point xn from one dimension, for example, small d dimensions, and then you're going to take it to the capital D dimensions, the higher dimension, different reverse action that we did in PCA, right? From a small dimension to higher dimension. And in that higher dimension, it's just giving you the right embedding, right? The right features that you need in order to do the linear classification, right? Great. So this is pretty much a general recipe for any nonlinear problem. So if you have any nonlinear problem, you can always do linear classification on the higher dimension model. Higher dimension representation of your data. Okay? Now, at the end of the day, you have your embedding, this phi. And out of this embedding, what you want to do the classification. You are going to use SVC, right? Because this is the best linear classifier that we found. So I'm going to put this phi here. I multiply it with the model. So obviously, the model should be same dimension as the number of features that I have extracted. And then I classify checking the sign. Yes?
Is that mathematically equivalent to a nonlinear classifier?
Yes, it is indeed. Yes, but I mean, when you talk about nonlinear classifier, there's no unique answer, right? Or unique formulation of that. It's not like a line, right? Linear classifier, right?
Yeah,
so
maybe whatever was the corresponding higher dimensional space that you...
Right, yeah. But when we represent in this form, then as we go on, we can use whatever we have done in SVC to solve this one, and then it's going to give us the kernel trick, which helps us getting rid of this phi function, because we don't know what is phi function, right? I gave you one example here, but you don't know in general what should be phi, right? Make sense? Okay, yes?
How do we know there must be linearly separate situation in a higher dimension?
Well, you don't know, but you can say that if I go very high dimension, I can always do this.
That's just assumption.
It's not assumption. I guess, I mean, like if you can theoretically go to infinitely high number of dimensions, right?
Yeah.
Then you can definitely do that. You can show this mathematically. Yeah? But the point is that finding out that phi is not easy, right? So we need to get rid of that. We use kernel trick. It's going to help us do it. But the issue that is going to happen is that we don't have control on many things. And then again, there's no guarantee that this happens in practice. But theoretically, if you have, I mean, it doesn't matter. I mean, what is? Like your data is just jumping up and down every second sample. It's OK. I mean, just go to infinitely large number of dimensions, right? So it's going to be so huge. Like I can, if I say this is plus minus, right? So if I have infinite order, I can always write down one polynomial of order infinite, which is always passing through one, like it's just jumping plus minus every interval, right? And then I'm going to perfectly classify my data. See my? The order of your polynomial. If I have something like the example we had on the board. So if I have this, this is my x, right? And say here is plus, okay? Here is minus. And here is plus, here is minus. So my classification problem is as complex as this one, right? So every short interval is changing the sign, right? So I need one nonlinear function like the one we did that is going to pass like this, right? Right? And if I have infinite order for polynomial, I can make this, right? Because I can change the curvature as much as I want, right? Like for this one, it looks like a sine function. That's OK. But in general, if the intervals are changing, then I still can do it by a polynomial, right? But the order of the polynomial could be potentially infinite, right? This means that I get x, and then the first dimension is x squared. And like the original dimension is x, right? The second dimension is x squared. The third one is x cubed. The fourth one is x to power 4, and so on, right? And if I am able to just take it to x infinite, right, then I'm going to have this huge feature. And that one definitely going to classify it linearly, right? You get it? Make sense? OK. Questions? Everybody's cool? OK. So now let's think about this particular example that we had before. So we have two-dimensional data points, right? Some of them are red. Some of them in the middle are green, right? So I want to find out if there is a way to use the same trick as we did before. Do you have any idea how I can do it? Yeah? Third dimension, right? Go up, greens remain down, right? You see this? So if there is this problem, right? And you really do know where are the regions, right? You don't really need to go for infinite order, right? Just get the red ones, take them up, keep the green ones down, right? And then there is one plane separating them, right? So if you think about this guy, now I'm trying hard to show it three-dimensional. So here, this is like I'm thinking about x1, x2, and then there is x3, new dimension, right? I'm not showing it here because still the data is in 2 dimensions, right? But if I'm able to compute the third dimension such that the green points remain down, the red points go up, then I have one plane to separate them, right? Everybody sees what we're doing? Questions? No question? OK, so this means that if I can write the right phi, this can take this 2-dimensional point, put it in the 3-dimensional dimension. a three-dimensional space, so compute the three-dimensional feature, and out of that feature, I can simply compute a linear classifier, right? And that linear classifier would be the SVC, right? So now that things are clear for you, the support vector machine is essentially the support vector classifier when it's applied on the higher dimensional features extracted from the data point, right? So the way that you would do it, you just do SVC, but instead of working with X itself, you just work with a high dimensional representation of it, right? This phi. And this is now capable of learning nonlinear features or patterns inside the data, right? Now, that sounds quite interesting, right? But is there any issue here that we cannot address yet? Yep. Phi, right? Inverse? No, you don't need inverse. Because if I want to do the classification on new data, I get X. If I know phi, I put it inside phi, I get the feature, I do classification, right? There's no need for its inverse. But I need to know phi, right? But why you need to, right? For example, I give you an image, right? The image has 100 pixels, right? But you say, I cannot work with 100, I need 1,000, right? It's okay, you get the 100 pixels, you compute the 1,000, you're going to tell me it's a cat, right? That's over, right? You really don't need to get back, right? So the problem is not by getting back, the problem is that we don't know this, right? So I gave you some simple examples that you can imagine, but the question is that is there a way that we can algorithmically find out this embedding function? Yep.
Do we know even what dimension we need to go to? Or
No, we don't know that. Right? This is also a good point, right? You don't know what dimension. Maybe you can guess like, okay, if I go significantly high, then it works, but you don't know what exactly you should do. But it turns out that you don't need to know any of that. Yeah. Yeah, but that's going to be crazy hard, right? Like if you want to classify image, right? This is impossible. I mean, old days with basic data, people used to do that actually, but nowadays, no, you cannot do it. We do it by neural networks. Questions? Okay, so the key challenge here is that how we can find this embedding function, and now the answer is very promising. You don't need to know it. So if we want to, like this super high, first of all, we don't know what is this function, and as your friend mentioned, we don't even know what is the right high dimensional feature that we need. What is the target dimension that we should go for, right? Okay, now, let's just write down the SVC classifier for this case and see what's going to happen, right? So if you remember, when we wanted to find out what is the support vector, then we just solved this problem, right? So we had the dual variables, lambdas, and they are getting multiplied with the labels and this term, right? And then we just build this optimization problem. It's a quadratic optimization problem. We can simply solve it. And then we're going to solve it. Bunch of those lambdas are 0, so they are not support vectors. Bunch of them are non-zero. They are support vectors, right? And we're going to collect that, right? And then once we collected that one, then we're going to take our model and we write it down in this form, right? So the summation of those lambdas, which are mainly non-zero for support vectors, times the support vectors, right? Superposition of the support vector. Now, if I want to classify a new sample, if I give you a new sample x, what you're going to do, you're going to get this x, multiply it with this w, and check the sign, right? Which we wrote it in this form, right? And now we talked about it, that here we are only checking the cross-validation, right? Everybody's following? Cross-validation, the green term, right? The inner product of the data points. Cross-validation, this inner product, right? Everybody's cool? Okay. So we only need to do the cross-validation, correct? And now, what if we are working with the higher dimensional features? Okay, I am going to do the same thing, but this time instead of my data points, I am going to have my higher dimensional features, right? This means that instead of x, I'm going to keep phi x here and here, right? Everybody's clear? Right? Now, this is the optimization problem that I need to solve if I want to write down the SVC for the higher dimensional case, right? And if I want to do the classification, what I do, I'm going to write down the linear model in this form, right? The superposition of the support features, right? And then this guy is getting interproductive with the embedding of the new data point, right? Now, one question, do I need phi itself? Do I need to know exactly what is phi? No. What do I need to know? Phi transpose times phi, right? The inner product of phi at one point to itself at another point, right? This is the only thing that you need to know, right? Phi is high dimensional, right? What about phi transpose times phi? It's just a number, right? It's just a scalar. Inner product, right? Is the cross-validation of the features, right? You see that? You get it? Okay, so the key point here is that you don't really need to know phi itself. The only thing that you need in both training, in both finding the right model and in doing the classification is to check the cross correlations, right? And the cross correlation is a very low dimensional function, right? I mean, phi could be 1,000 dimensions, but phi interproducted by itself at another point is always one number, right? This guy, this inner product, is what we call it kernel, right? The kernel of that feature space, right? And it says that if I know the kernel, which is a scalar function, it's enough for both training and classification, right? Everybody's cool? Questions on that? No question? Yeah.
So in SVC, in this scenario, the idea was that because we never actually, we always got a value for that expression instead of the actual individual components.
Right.
That's how we got to. So it's the same scenario here where we get a value for the full expression of W. Like, we don't actually need W star, we just need the cross correlation.
Exactly, yeah, that's the point, right? Because W itself is written in terms of the support vector. At the end of the day, W times the features is basically a superposition of the cross correlations, right? And that's enough, right? Everybody's cool? Questions? Okay. So, kernel trick, this is the idea that I mentioned here. So you only need to know the kernel. And once you know the kernel, you can do both training and classification using this new SVC. So this is the idea of kernel trick. So we don't really need to work with the high dimensional space directly. It's enough that we know the embeddings and how the embeddings are correlated. Basically, we just need to know the kernel function, right? So this is what we call a kernel. So the kernel is a function which is taking two different points, right? xn and xm, 2 points. And then it's going to compute a sort of cross correlation between them. But this cross correlation does not need to be necessarily linear, right? So if I tell you compute cross correlation between two vectors, you just simply interproduct them, right? And but you don't really need to do that, right? It might be more complicated function. And you can think of that function k to be actually one feature in a huge dimensions times one other feature computed at the other point, interproducted, right? Everybody's cool? Now, if I define the kernel function, then that's it, right? I only need the kernel function. I can put the kernel function inside the SVC expression. I can do the training. I can do the classification, right? Any questions? Yeah.
Basically, it's like just a rephrasing of like the problem. Basically, instead of trying to find the phi function, which is like maybe.
Yes, but k we can assume something, right? For example, x, you have x, right? This is your data point. And you could say instead of inner producting them, I get x1 and I inner product it with x2, then I square it, right? This is my kernel. Why? Because it's higher dimensional, right? I give you a couple of examples, you're going to see that. But this is now feasible to do, but that other one is not feasible. You cannot find the phi, right? Questions?
Kernel just takes 2 samples.
Right?
So just 2 sample points or sample data?
2 data points. It could be sample from your data set. It could be a new point, right? I'm going to show you when you want the new data point, this one, let's take a looking at this one. This guy is the new data point, right? When you want to do the classification. And then you need to compute the kernel between your support vectors and the new point, right? That is going to be the classifier. If you want to find the lambdas or the support vectors, you need to just compute the kernel between the 2 different samples from your data set, right? Make sense? But you need to have a function which is able to look at 2 different points, 2 distinct points, including a point itself with itself, right? And compute the kernel, right? So the inner product does it for you automatically, right? If I give you 2 points, you just compute the inner product. But you can think about more advanced kind of function, right? So essentially, if you take the kernel trig, then your training is going to look like this one, right? You're only doing cross-validation. So when you want to find out lambdas, you basically build this optimization problem, right? You're going to have a bunch of cross-correlation between 2 different points. You compute those cross-correlation, and you build this quadratic function. You solve the optimization. You find lambdas. A bunch of them are 0, so they are not support vectors. A bunch of them are non-zero. And final model is supposedly the superposition of all of those support features, right? But you don't really need to know the support features as well, because if you have a new data point, then you simply need to get the kernel. You take the support vectors, you check the correlation between the new point, and then you build this term and check the sign, right? This is going to do the classification for you, right? And it can potentially do nonlinear function now as well. Questions? No question? Okay, great. So moral of the story, SVM is basically SVC, but this is going to work totally nonlinear, right? The key factor here is that instead of doing linear cross-correlation, you're doing nonlinear cross-correlation. And by doing that, you can potentially get very complicated problem solved, which was not possible to be solved by linear classifier. Everybody's cool? Questions? Okay. Great. So if you want to think about it, you have this case which is nonlinear. Then basically you have the kernel function, right? And this kernel function is going to look at 2 different points, right? It could be any point in this space, right? It's probably going to look at these 2 points and compute the correlation between them, these 2 points, and so on. And then it turns out that these guys are support vectors, right? There is no reason for you to have that nice line and margins anymore, because nothing is happening in your own space, right? You're working in the feature space without going inside that, right? And then in that feature space, these points are somehow getting expanded, and they become the support vectors, right? So if you want to think about the 3-dimensional example that we had, if these guys go up, then the red one that I show is probably below the plane, and the green ones are the nearest one above the plane, right? And then your plane is passing through them, right? Everybody's cool? Great. Now, if you get a new point, what you're going to do, you're going to check it with every single guy, right? Using your kernel function, right? And out of that, you can classify, right? So you check with this one, it's going to give you a correlation, 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 and then you're going to decide which label it has, right? Everybody's cool? No question? Great. So if you got no question, then let's get into this question, that what is, sorry guys, I guess I need only 15 minutes to finish up, right? So I guess the time is okay that I keep on going and then we finish the lecture, right? Instead of having a break, because it doesn't make for 15 minutes, right? Okay, great. So let's just talk about this part, how we can specify the kernel, right? And if you want to specify the kernel, this is a big question, and actually nobody knows what is the right choice of kernel. The initial idea was that, okay, let's go for complicated functions, right? So for instance, people started to do polynomial function. Can you guess what does it do, really, this kernel? So you get 2 points, you compute the normal correlation, you add up a constant, and then you take it to power p. Okay? What does it do? Do you have any idea? What kind of embedding you would think that is happening? Like, let me just consider this case. Let's say that x is just one-dimensional vector, right? X and xm, right? The inner product is simply the multiplication of them plus some constant, put it 1, and then you do the square, right? It's going to be first guy squared 2 times this guy plus 1, right? And now you can decompose it, right? If you decompose it, you can put all of the xm's in one vector, xn's in another vector, right? You see that? And then this is basically the inner product of those 2 three-dimensional vectors, right? Now, if you think about this guy, the fact that the thing that you are doing, you get your vector, and then you put it on a polynomial, right? This means that you are somehow extending the dimension by getting the vector itself and then computing all of the polynomial orders, starting from order 0, right? Order 0, order 1, which is the guy itself, order 2, order 3, and so on, up to order p, right? And then you inner product those guys, right? Everybody sees that? So you had a vector, now you have a matrix, and that matrix contains all of the features that you need, right? No, because you do not compute this one. You compute this one, right? Okay. This is the whole kernel trick, right? You don't really need to go in that dimension. You work in your own dimension, right? In your own space. Make sense? Yeah. But since you asked this, this sounds quite promising, right? Because if I put p quite large, this is going to be huge, right? But do you think that it's going to work? Like, it's going to beat everything. What is the challenge here? What is the issue here? Especially if you have done anything with neural networks. Yeah? It's not about it could overfit, that's right, but it's not about overfitting. You don't have some degree of freedom here. Any idea? The coefficients that you see here, 1, square root of 2, 1, they are just imposed by the choice of kernel, right? But you do know, those of you who had, we're going to have it in this course also, those of you who work with neural networks, the whole magic of neural network is when you can play with the weights, right? So it doesn't mean that if I take it to the higher dimension, necessarily I'm going to get the good representation, right? It could potentially be the one if the weights are right, right? But in neural networks, you have this ability to play with the weights, right? Here you don't have. Why you don't have? Because you want to work in your own data domain, right? You don't want to really find out what are the features. You just want to find their correlation, right? And this is the price that you are going to pay. Everybody's cool? Questions? Yeah.
So when using
Yes, yeah, essentially, yes. So we're going to get quickly into the part where we check generalization. Then you are going to get this one, try it on your training data set. And once you are finished training or doing finding the support vectors, then you try it on a validation set. If it works fine, that's okay. If not, you repeat this, right, till it converges, right? But the point is that if it doesn't work, I mean, C is not going to do that much here. The only thing is P. And then if it does not work, you need to, for example, go for higher P, right? It's not like you can play with anything. By neural networks, you can play with that, right? You don't need to go for higher dimension. You just change the weights that show up here, right? Because they are the weights of the neurons at the end, right? Okay, great. So this is indeed the embedding that we did before when we wanted to just talk about that cat or dog problem. We just took the one-dimensional guy. We took it into the second dimension. The second dimension was the square root of that. It's going to have this constant. This is not important. You can simply ignore it, right? Because it's constant for every vector. And this is pretty much what we did before, right? So this is why we call it a polynomial kernel, because it's essentially somehow computing a polynomial vector of features, right? Now, another guy which is very popular and like still many people use it when it comes to data analysis is this Gaussian kernel or radial kernel. So what is this guy? This is essentially you get x1 and xn and xm, two different vectors. You compute their distance in the Euclidean norm, okay? And then you take it to this e to power in the exponent of this function. So this is the distance minus distance divided by some sigma. This is the exponent, and you compute the kernel to be e to power that, right? This is obviously, again, a valid kernel. I mean, you can see that this is always non-zero, right? Sorry, non-negative, because it's an exponential function. And you can guess why we call it, oh, sorry, this should not be order. Oh, sorry, this is a copy-paste. Yeah, bad guy doing. Okay, sorry for that. This is the polynomial. It's the same thing as this one, right? I just copy-pasted. Sorry, this is a Gaussian kernel, right? Sorry, it doesn't have any order. So you can guess why we call it Gaussian, right? Because the expression you have looks like a Gaussian distribution, right? But thinking about this one, what do you think is the embedding space or embedding dimension? Any idea? It's good to think about it. It's not log, no. What is the dimension size, I mean? Like in the polynomial case, the dimension size was p, right? If I give you x, then you have x squared, x cubed to xp, right? So the dimension was expanding by factor p, right? What is the dimension here?
How would you go about answering that question? Like, what would you think about answering that question?
Just if you have any idea, I'm going to show you the answer. No worries, it's not a quiz or something, right? Just wanted to, if you see that, right? Okay, so it's actually infinite dimension. You're taking your point to infinite dimension. And what is the reason? Well, you probably know the Taylor expansion of the exponential function, right? E to power x is 1 plus x squared by 2 factorial and so on, right? And it goes forever. It never stops, right? Now, if you write down that guy, you can go ahead at home, put xn and xm, both of them, and another typo from Mr. Typo. This 2 should be out of the norm, sorry. I mean, this slide, you just throw it away, full of typo. Yeah. I didn't tell you this lecture. I used to be called King of Typo. Everybody has a name, right? My name was King of Typo, right? So, I mean, nowadays with ChatGPT, you should not have typo, right? But you can guess that I'm not using ChatGPT, obviously, right? So, if you take this guy, you put xn and xm to be scalar, and then you take that second norm, and you expand that exponential function, then you are going to have all of these terms. And these terms turn out to be like 1. Then one term you have x and xm. The other one you have x and xm squared with a bunch of coefficients, right? And so on. And then you can think of, you have infinite dimensional vector, feature vector for xn, infinite dimensional feature vector for xm, and then you are inner producting them, right? This is the way that you are computing your cross correlation. Does it make sense? Questions? Okay, now one thing that this guy tells you, I mean, if you go ahead and use this one, it works to some extent, but it's not solving complicated problems, right? And this is telling you something obvious, that simply going for huge dimensions is not the solution, right? It obviously helps, but is not the solution, right? You see that? Because I have done this by this function here. It's theoretically taking me to infinite dimension, right? But still, it's not solving the problem completely. Whereas the same problem, I can solve it by a neural network, right? Now, again, the issue here is that I have no control on these coefficients, right? This coefficient 1, 1 over 2 factorial, and things like that. I have no control on that, right? This is happening by kernel itself. I cannot change it, right? Now, if I want to get rid of that or somehow resolve that issue, what should I do? Introduce a bunch of coefficients to that kernel, right? Maybe I define the kernel, but put some coefficients which I leave them like tunable, right? And then I try to find the right coefficient, right? Doing some optimization. Everybody's clear? You see that? So this is the idea. So what is the good kernel? Nobody can say. We see that if we go even for infinite dimension, that is not the solution necessarily. Now, what is the answer? Now, maybe we can come up with some solution, which is just understanding from the data, like introduce some bunch of weights and parameters into our kernel, and those weights are going to somehow get tuned so that we get the right kernel, right? So there had been a quite long story on the feature engineering. So if you define, I mean, what we are doing right now here, we are defining a predefined kernel. When we use a predefined kernel, we are doing feature engineering, because by setting the kernel, we are somehow imposing some constraint on the embedding, right? And we have no choice in changing that embedding, right? This is what we call it feature engineering, and there had been a very long, very large literature decades ago that people try to find the right feature engineering, right? Like trying different kernels and say that this one is working better as compared to this one. The reason is because a bunch of coefficients are more dominant here, they are not dominant there, and so on, right? But at the end of the day, it didn't work like universally work in solving all the problems, right? Now, is there another way? Well, this was a question people tried to answer. And this sentence that you see here in the quotation mark is what Vapnik said in his paper. And I mean, as I said, nowadays it makes total sense and everybody agrees with that. But at that time, people were just laughing, right? Let data speak by itself. This was his idea. Okay, we do not really need to try to engineer the feature or find the right kernel. Maybe we use a bunch of parameters and we'll let the data, through some optimization, we'll let the data to somehow decide for those weights. And probably the data are going to say the best thing. We are not the one who is capable of doing it, right? So the idea here is that I can decide for one kernel which has a bunch of tunable parameters. I'm showing it by theta, right? For instance, in the Gaussian kernel that I showed you, I can leave the parameter sigma to be learnable, right? To be tunable, right? So I do not say that sigma should be 1, 2, or anything. I would leave it to be open, and I would say, okay, I want to find the right choice of sigma in that, right? Or in the polynomial one, you can think of C to be tunable, or you can introduce one coefficient getting multiplied also to the inner product, and then you train that one. You find that one, right? Or one easier thing that people used to do, instead of applying your kernel directly on these data points, you first transform your data to another space by a linear transform, right? So you would say, instead of having xm as my data point, you multiply xm by one matrix w, right? That you just leave it to be tuned, right? W times xm is my represented data point. W times xn, the other represented data point, I put it inside the kernel. Now I compute the cross correlation, right? And that w is free to choose, right? Everybody sees what I'm doing? What I'm saying? Yeah? So this is what we are going to do in neural networks, basically. Yeah? But the idea somehow is rooted here. So the idea here is that you specify this theta, then you tune that. And if you want to tune it, we can get back to that risk minimization idea, and we write down the risk that we compute. And now this risk depends on both the coefficient of the classifier, w, and those parameters that we leave tunable inside the kernel. Right? Everybody's cool? Yes?
You said coefficients of the classifier for W? It's not the
No, this w is the one which you find by SVC. Right? I mean, at the end of the day, you are going to write it down in terms of the support vectors, right? You already know this. But then you have a bunch of, all of those terms that you compute depend also on theta, right? Because if you get back here, here, right? So if this k, the kernel function, depends on theta, right? This term is going to depend on theta. I can fix theta and solve it. I'm going to find the right w, right? But then that w depends on theta as well, right? Now I can try my w on my data points, and then I pick the theta, which is giving me the minimum value. Everybody's cool? Now, you might have this question, how we can do it. This is what we're going to do on Thursday. I'm going to explain you a gradient descent that you can use it to minimize any function. Okay? But right now, you assume that you have the algorithm to solve that problem, right? If you have that algorithm, then essentially you find this guy, and then you leave it free for theta, leave it general theta here, and finally, you just solve an optimization problem. Questions? No question?
Can we add more than one parameter, like theta?
Definitely. I mean, here theta is bold. I mean, a vector of parameters, right? But definitely, I mean, early days people were introducing a few ones, right? But gradually they understood that it needs a huge number of parameters, right? Everybody's cool? Questions? Now, one question here. This problem, like if I put theta inside the kernel, for instance, inside the Gaussian kernel or polynomial kernel, when I get into this optimization problem, of course I can solve it in terms of w because this is a constrained quadratic function, right? Optimization. But in terms of theta, is it necessarily a convex function? No, it's not, right? So this was the point that people stopped decades ago. It's not a convex function. You cannot solve it. Forget about it, right? What you want to do? Gradient descent? Ha, ha, ha. It's not possible, right? For a long time, people said this, right? Till they started to do experiments and it started to work, right? Now, it's interesting to think why gradient descent is working when the model gets complicated. That is, like those of you who have some courses on stochastic optimization probably get a bit of idea on that. But at that point of time, people did not have this perspective. So they did know that if you want to solve this optimization problem, this is generally non-convex, very complicated. You might be able to use gradient descent to find a local optimum, but this is definitely not the global optimum, and it's useless, right? And they tried some simple parameterizations. They did it. It turned out not to work very efficiently, very significantly, and they said, okay, leave it. This is just an idea. It's not going to work, right? When people were working in this form, this was the idea. They used to call this domain representational learning. And the reason that they call it representation learning was because they use this kernel, the parameterized kernel, to find a sort of, implicitly, not directly, implicitly to find a feature representation of the data from data itself, right? Because kernel is somehow computed from features, right? And now you're setting kernel to be a function of theta. This means that your features are function of theta, right? And then you solve an optimization problem on theta to find the optimal choice of theta. This means that you use the empirical risk minimization to find out what is the right representation of data in the feature space, right? And by doing that, you're somehow learning what is a good representation. Everybody sees that? So this was the representational learning, and it was a quite long story. So yeah, this is what I already told you. So in the Gaussian kernel, you can leave sigma to be trainable or tunable, and you can find it jointly with W. That is not going to be a very complicated problem, but at the same time, it's not very efficient. Okay. Now, you can guess that this term representational learning, when it's given to a domain, this means that people have done a lot of work on that. And if you're interested, you can check the work by Bernhard Schulkopf. He is in ETH Zurich. So he was one of the, he was Vapnik's student, and he did a lot of work in kernel learning. So he wants to find out what is the right form of kernel and how you can well parameterize it, and why some parameterizations are efficient or why some of them are not. But then at some point, people said that, okay, this was a theoretically known result, but people saw that if you keep on repeating the linear transforms, and then you do a minor nonlinear operation on that, and you repeat that again, that sort of construction of representation is going to be efficient enough. So have you heard, or can you imagine what I'm talking about? I get my data, I linearly transform it, right, with a bunch of parameters. Then I do some nonlinear operation. I again do that, right? And I just go to higher dimensions if I want. This is a neural network, right? So the neural network, it's a kind of representation, right? Because I start from X, I do a bunch of linear computations, right? We're going to talk about it in the next part of the course. Linear computations, then we just activate, right? And this is a minor nonlinear operation. After that, we again do a linear operation, we activate, right? And so on, right? And we do it as much as we want, right? Now, if you think of these multiple layers, you can pack all of them as a function, right? And what it does is start from your data, right? And it computes a feature representation for that, right? And this is hugely parameterized, right? Because you have lots of weights here, right? So people started, by experiment, they started to see that this guy is very efficient because the problems that they could not solve it by kernel learning, this guy could solve it, right? And again, initially people started to say this is just a random accident for some specific application, but if you go on, it's not going to work. But they went on and it proved them wrong. So this guy somehow became dominant. Everybody's clear? Yes?
So at the end of the day, after all of these operations, we're still using SVM to classify our data?
Yes, but if you think about a simple classification problem, this is also the case that you do it inside the neural networks. But actually, instead of using SVC, instead of using SVC, you could, the features get rich enough that at some point, if you just use a basic classifier, like you don't do the maximum margin, without even the maximum margin, it's still going to work. Like that maximum margin thing is not going to be crucial at all. Yeah. But like with simple kernels, that turns out to be very, very important because it helps generalization in that case. Questions? So the key point was that if you use deep neural network, you can actually get that very right representation of the data that you want in higher dimension. And this key observation says that neural networks are actually a very good representation models, right? And this is why deep learning became the dominant area in machine learning nowadays. So one thing that you might understand, I guess you can understand right now, is when we are talking about machine learning, we are very general, right? When I tell you representation learning, I am just focusing on this idea that we talked today about, right? You have your data, you represent it in higher dimension, and then you use that representation to do your inference, right? And now, if you talk about deep learning, you are making things more narrow. So you are using a neural network, deep neural network, to compute those representations, right? This is why we say deep learning is a subset of representation learning, is a subset of machine learning. Is there another subset for representation learning? Yes, kernel learning. Like you work directly with the kernels, as I told you today, right? Old days, people had, like, the rest of this lecture should be about kernel learning, but nowadays we don't do it anymore because really it's not that practical. But if you're interested, as I said, just go ahead, type it in Google, see a lot of papers, and you see that at some specific period of time, many people spend time on that. It does not mean that they are useless. They're actually used in easier or more specific form of data analysis. But for most practical applications that we have nowadays, deep learning turns out to be the key, the winner. Okay, so this is the reason that the next part of the course is going to be about